Okay, welcome back. We now have Huon Wilson, who will be telling us about Follow the Postgres Brick Road, a journey of testing against a real database server. Now, Huon is a software engineer aiming to make others more effective. Please make him welcome.
Thank you. Welcome to the land of Oz, where the munchkins really like databases and the quadlings can't write enough automated tests. I'm Huon Wilson, and this here is Toto, Sterling, our corgi. I'm a lead engineer at Exoflare, which is an Australian startup working in biosecurity and in particular agriculture. We're making Australia and the world more resilient to biothreats. At Exoflare, I'm mostly writing Python. So that's back-end web APIs, event processing, anything server-side in Python. We use Postgres as our data store for this. And we use the SQL Alchemy library to connect to it. So I'll be talking about those sort of specifically in this talk, but hopefully some of the concepts here apply no matter what tools you're using. Maybe your framework already supports some of this, but like you now understand what's going on. I'll be carrying you along a bit of a journey. First, we'll talk about some principles to think about when you're writing tests, automated tests like unit tests, integration tests. Principles to think about when you're writing those sort of tests against a database. Why you might want to use just one database management system, how you initialize that database for tests, how to make it faster, and then a single specific test that's really helpful. Our first stop on the journey is with the Good Witch, and she has some words of wisdom for us. The first one is think about reality. So when you write code for users, you deploy it to production. That's where it's helpful. That's where code really matters. Any tests you write are hopefully giving you some assurance, some suggestion that the code in production will do the right thing. What this means is that you should, unless you have a really good reason, have your testing environment match your production environment. Your testing code match your production code. Try and keep those two aligned as much as possible. The next principle is independence. It's really helpful when your tests can run independently. So maybe you want to run just one test file by itself, or just a single test within that file. If you can do that, then you can iterate faster. You don't have to run your full test suite every time you make a change, you just run the specific relevant tests to you. The final one is hopefully uncontroversial. No one likes a slow test suite. When you're thinking about building testing infrastructure, make it fast. On our journey, the next witch we meet is SQLite. So somewhat embarrassingly, when we started at Exoflare, we had our production system, servers talking to Postgres, and our tests working with SQLite internally. Why did we do this? Well, SQLite is standalone. You've maybe just written import SQLite 3 in Python and you've got started. It comes with Python. You don't have to install anything on your system. You don't have to get it running. Don't have to configure it. It's just there. Really easy to use. The next one is that SQLite makes independence easy. So for that principle of independence, with SQLite, it's easy to just have each test work with its own database. So you can connect to a SQLite database in memory, and it's completely ephemeral, completely transient. You start your test, work within the database, chuck it away at the end. Your next test does the same thing in its own little ephemeral world. So you get independence. That's good. And it's efficient. SQLite runs in process, in memory. You're not having to do network round trips for every query. So when you've got very small data sizes, like you typically have in a test, getting rid of all of that overhead makes your test runs faster. However, in this context, SQLite is a wicked witch. And that's got an asterisk because it's not actually wicked, it's really cool technology, or maybe it's this sort of wicked. But in this context where we had Postgres in production and SQLite for tests, that's not a good combination. Postgres and SQLite support different dialects of SQL, so different syntax, different functions. This means that we were writing queries that had to cater to the lowest common denominator. So queries that were bigger, more complicated, and ran slower than they needed to. So production was sort of behaving worse because we had SQLite for local testing. More subtly, SQLite is actually more relaxed than Postgres. So I think, at least by default, the types on columns in a SQLite table are more like comments than anything useful. So maybe you've written your code and you've made a mistake where you insert an integer into a string column. SQLite will happily say, yeah, that's fine. And you run your tests, they all pass, you deploy your code to production, Postgres says, what are you doing? It doesn't make sense, try again. You've written a bug, you've deployed it to production, and things aren't working. Your test suite hasn't helped you. Fundamentally, the problem with SQLite in this context is that it's not reality. It's violating that reality suggestion, and probably not for a good reason. Luckily, we know how to deal with witches. We can chuck a bucket of water on them, and they melt away. It took us several years to finally chuck a bucket of water on our SQLite tests, and not too long ago we got rid of them. So now production and testing looks more similar. Great. How do we actually make that work? Well, before we talked about how SQLite is standalone and Postgres isn't. Well, what we do is we start a empty database server. We've got Docker Compose, defines what Docker image we use, Docker Compose up. That gives us all that we need to get started. So I just leave that running basically for months. However long my computer's up has this Docker server running in the background. And then every single test run we do will connect to that server and configure whatever database it needs. So it's the test runs that are responsible for creating tables, for initializing anything. The database server just needs to be running in the background. This means that we don't have to remember to update the database when we've made a change to our schema. The test run manages that. Let's zoom in on how that actually works. So we've got a user object in our system. Hopefully you've got some users. And there's some tests about users. Presumably those tests will talk to a database. We use PyTest, so we've got a PyTest fixture that connects to the database. So presumably it's running on localhost, we have a fixed port, we put in the appropriate connection string, get a connection to the database. And then we can actually create the tables. So if we need tables in our database, if we need indices, all of that happens in this fixture. How do we do that? Well, there's two options. With SQL Alchemy, you can define models. So like a set of Python classes or objects that specify what the table should look like. Maybe you've got a user table, maybe you're working with pets, so you've got a dog table too, and whatever other tables your database needs, you take all of those classes and just splat them into the database in one go. Like, create me these tables, please. The other option is migrations. So imagine, let's not think about testing now, let's think about our production system. Years ago, you started your production system, you started with a few basic tables. And then, as requirements came in over the next weeks, months, years, you had to add new features. So add new tables, add new columns to support those features. Maybe you could get rid of features, so you get to delete tables and columns as well. All of those evolutions to your schema to support your new code has to happen as incremental migrations. So like, here's a piece of SQL code that will migrate my database schema to add a new column to this particular table. This is how production works. And sorry, I don't have time to really go through migrations. If you're not familiar with them, you should go work on understanding them because they're a really powerful concept. But anyway, that's how production works. So now going back to our original question of how should we initialize our database for testing? We've got models and we've got migrations. Let's think about the reality principle. Migrations are what happens in production. Therefore, migrations are how we should initialize our database for testing. Instead of running from start and then all of the migrations since then, we can just, over many years, we can run them in one sitting. So when the fixture starts up, connects to the database, starts with the first migration, runs all the way through to the current final migration. Maybe you've got dozens or hundreds of migrations, and that can take a little while. For us, it takes about 3 seconds. So 3 seconds from starting, connecting to the database to having a database ready to use for our tests. with the efficiency principle in mind, how can we make that faster? Well, we all like hard problems, so let's do some caching. Imagine we run tests once and they fail. We've made a typo in one of the assertions or something like that. So we go and edit our code and we run tests again. Naively, the first test run will spend 3 seconds running our database migrations. We've edited the code. The next test run will spend 3 seconds running our database migrations. However, we've only edited code here. We haven't changed our database schema. So we can try and reuse the work the first test run did in the second one. That first test run will sort of squirrel away a cached version of our schema into the database server that's running there. While the second test run can realize that, oh, there's a cache here, the work's already been done, I'll just use that. So instead of taking 3 seconds to run migrations, that second test run gets started in like half a second or a bit less, just by copying from the cache. That's a nice win. How does it work? Postgres has create database called test for this example, template, and then another database name. So that's another database within our database server, just a normal database. We can use any database as a template, and this has created the test database while sort of copying the schema, so that means the tables, the indices, all of that, as well as even the data, I think, across into our test database. And then test is independent of the template it was created from. But there's a subtlety here. Whenever you have caching, you have to think about invalidation. What if we edit our migrations? So we've been running this, then we realize that, oh, we need to add a new column to a table. So we've edited our migrations, then we run tests again. That test run can't use the cache that we just created because we've changed our database schema. So reusing the cache, which has a particular set of tables, would be wrong. They don't have the right shape. Luckily, migrations are, at least under SQL Alchemy and Alembic, they're just a bunch of files on disk. So the files on disk specify the state of the database after running those migrations. And you can take a hash of all of those files. So you key your cache by the hash of the migrations. So on our first test run, it was like, I'm about to run these migrations. Let's take a hash of them. We get ABC123. It checks the database server. Oh, I don't have that cache. I don't have a cache yet, so I better run migrations. I'll run the migrations and then save a copy under the ABC123 hash. The second test run will do the same operation. Okay, I'm starting up. I've got a set of migrations. I'll hash them. I'll get ABC123 again. I'll look in the server and see I've got a cache already. Then it can work faster. Now the third test run, that's the one after we change migrations. So that's starting with a new set of migrations. It hashes them. It gets a new hash, DEF456, let's say. So that doesn't exist in the server. It will do the same thing as the first test run, where it creates a new cached copy under the new name. Then our future test runs get to benefit from that cache. So this is sort of thinking about that changing our database schema is less common than changing our code. So by caching our schemas, sometimes we have to pay the migration cost, but not always. We get to optimize the common case, cut the time from 3 seconds to like half a second. Let's zoom into actually running a pair of tests. So we're thinking about our users again. We've got add users on the left and list users on the right. Presumably you need some functionality to create new users and some functionality to search them. If we're not careful, it would be easy to violate our independence principle. So if we run the add users test first, we insert something into this table user. We run the list users test and it selects from that same table. If we're not careful, we could be selecting the data we just inserted in the separate test. We're hoping that they're independent, but we've accidentally made them not. So we might write assertions in our list users test that won't work when we run it by itself. So if we ran list users by itself, we're just working on the list users functionality, so we run the test by itself. We're now missing the data that it was thinking it should be reading, and our assertions are broken, and this test is failing for reasons other than the edits we made to the code. It's failing because we just ran the test by itself. So the tests aren't independent. That's not good. We should fix that. There's a few ways to do it. One sort of tempting way would be you create the database at the start of the test. You do whatever you need to in your test, and then you clean up. So you have a tear down phase, you have a cleanup phase, and you go through and delete all of the data you inserted. So for our add users test, we run things, we insert something into the table, and then at the end of the test, we say, okay, we're done now, let's go delete the thing we inserted. Unfortunately, humans make mistakes all the time, and so this is really easy to get wrong, where you might miss a deletion. So imagine the delete from wasn't there because you forgot to add it. Or you added a new table, like a helper table for the user data, and you didn't delete from that one. So in that case, you'd end up with the test accidentally being non-independent again. Another approach would be to move the database creation into each single test. So each test creates a new database, works within that database, and then drops it. Then the next test creates a new one. They each get their own independent database. They're automatically independent, but it's slow. Remember how I said it took about half a second, even with the caching, to create the database? If you've got 10 tests, that's 5 seconds just creating databases, not doing any actual useful testing, just initializing for tests. We want to make it faster, and we can. So we can use transactions in the sense of like asset, commit, rollback. We create the database at the start of our test run once, so we just pay that half-second cost at the start, and then we use transactions within each test. I'm just going to flip this around, so it's the same test, just flipped slightly, and let's work through what actually happens here. So at the start of our test run, we create a database. Then we start running the add users test. That begins a transaction, and that's sort of beginning from that pristine state when the database has just been initialized. The test runs, it does insertions, it does assertions, it does all the things that you need your test to do. And then at the end of the test, we can roll back. So the rollback is basically like all of the things that happened within this in the context of this transaction, chuck them away. So in essence, we've reset our database back to that pristine state when we created it. So all of the mutations that happened, they automatically get chucked away. We don't have to remember specifically, let's go delete this user. Let's go delete that item. And the same thing happens for the list user test. So we begin the test and it's starting from the pristine state. All of our database tests are starting from that clean database. We're not having to worry about independence. So the list user test does its thing, roll back, gets reset, ready for the next test after that. This is great, but there's a subtle error we can make that causes problems. This is a very similar test, but now we've added a new row. It says commit, and it's in blue because maybe it's hiding deep within your application code. So your test is calling an add user function or calling an add user endpoint, and deep within that, it's running a commit, and you're not expecting it to be there. Now what happens when we run this version of the test? We begin the transaction, we do the work within the context of that transaction, within the test, and then we hit the commit. So that commit will persist all of the mutations we've made up to that point. So our insertion is now saved into our database and is available for future transactions. Implicitly, a new transaction will start, and the rollback will just roll back that new transaction. So we've only rolled back to the commit. We're not rolling back what we expected, which was all of the mutations that happened within the context of this test. Now, when list users starts, it's starting from the data that was committed. So our tests are no longer independent, because that list users test is seeing the data that the add users test added. We've caused the same problem that we were concerned about before. And this one's quite subtle, because that commit could be hiding anywhere. Like, it might be deep within a call tree. So we've got good test on the left, not so good test on the right. How can we not make the mistake? Like, they're not that different, right? Well, let's talk about what we actually do. So look at our specific PyTest fixture that gets us set up, because it defends against this problem. So we'll just look at the add users test again. And there's two fixtures, in essence, that we use. The first one is a session scoped fixture. So session scoped means it only runs once for the whole test session. That fixture will create the database. So like connect to the database server, create the database, and then initialize the table. So it will do the migrations, it will do the caching as required, and then give us back a SQL Alchemy session. So we're now connected to the database and can start working with it. Should have had the highlight up. Oops. The next fixture is test or function scopes. This will run once for every test. This is what manages our transaction. So we'll start with that SQL Alchemy fixture that the first one created, and then it will begin a transaction. We need to begin, let's do it. We yield back to the test code. So that's where the test code runs. It can do all of its mutations using this session. And then we defend against the problem we just found. So the problem we just discussed, where there was a commit hiding in our test code, this is the trick that checks our test for us. So if the test code committed, the transaction we've started in this session is no longer active. That one's been closed off and a new transaction has started. So by checking that the current transaction, or the transaction, checking that the transaction this fixture created is still active, assures us that there hasn't been anything sneaky going on in the test. The test hasn't run a commit statement. If it has run a commit statement, this assertion fails, and the developer is told, your test is invalid. You either need to fix it or not use this approach. So there's some tests where you can't use this transactional approach, where you actually need to be checking commits and so on. And now the developer is reminded explicitly that they have to make that decision about how they're approaching this test. There's no room for human error here. Now, as a developer experience thing, there's a more subtle thing that we do. That fixture is almost exactly what we do. This is complicated. I'm not going to explain it, but it's up here for the video. So if you really want to know the details, you can either take a photo now or go and look at the video. It digs into the SQL Alchemy internals. It improves the experience if you write an invalid query, reduces the number of weird errors you get. But fundamentally, it's not required for verifying the lack of commits. Anyway, moving on, because that was complicated and I had to put it up there to feel like I've told you the right things. Once we've done that, we're assured our test is valid and we're assured that the rollback will get rid of all of the mutations that we need it to get rid of. Okay, I've talked a lot about this, but I haven't really motivated it. Why are we doing all this effort? Well, it takes about half a second to create a database. It takes 3 seconds to run migrations, but we already optimized that part. Half a second to create a database. With this, it takes like 10 milliseconds or less. So we've made it much, much, much faster. Databases are good at creating and getting rid of transactions. It feels like magic. You and I are all sorcerers and sorceresses. Thank you, munchkins. But it's worth the effort. Making our tests faster, really useful. The next piece of efficiency is parallelism. If you've got the tinsmith and he's broken and you need to repair him, you probably want as many tinsmiths as you can. One working on the arms, one working on the legs, one working on the head. If you just had one working on them sequentially, it would take longer. Same thing applies for tests. Imagine we've got our 2 test files, users, dogs. If we just run the test normally, naively, first users does its thing, talks to Postgres. Then sequentially, dogs does its thing, talks to Postgres. Your computer probably has more than one core, and if you run tests like that, you're only using one of those cores. Wouldn't it be nice if you could throw more cores at the problem and make your tests run faster? Well, we use a build system called Pants, and it means that we can run tests sort of automatically in parallel. So the test files run in parallel, but we've got this shared resource of the Postgres server. Whenever you have a shared resource and concurrency and parallelism, you start having to worry about race conditions and people stepping on each other's toes. Fortunately, the solution here is relatively easy. You have each test just work in a unique database within your database server. So your database server can administer multiple databases. When the tests start up, we had that raw session fixture that did the initialization. That just chooses like a UUID, random unique name. And then each test can work in its own little world and there's no interaction. So we've got parallelism without the parallelism problems. We've got fast test initialization. Let's look at a specific test that's helpful. So here's what a SQL Alchemy model looks like. Hopefully, even if you're not familiar with SQL Alchemy, you get the sense that this is a table called user, there's a name column, and it's a string. The models are handy for writing your Python code. So we use SQL Alchemy as like a query builder. You can type select, user dot, and then you get autocomplete. You get jump to definition, you get doc strings, you get type checking even. So the models are helpful in our Python code, but as we were discussing before, models are not how production works. Production uses migrations. Let's look at that in the context of a specific change. So a feature request comes in, we now need to be able to search for users with a certain amount of courage. So let's add courage as a column, it's numeric. When we add that column to our model, it's now available for our Python code to refer to, but we don't have it in our database until we generate a migration. So SQL Alchemy pairs with the library called Alembic. Alembic lets you auto-generate migrations from your models. Again, even if you're not familiar with the details of Alembic, hopefully this makes sense. When you run Alembic upgrade, it will run these upgrade functions, and this one will add a column to our users table. Column's called courage. So we've got our column for our Python code, like in our model. We've also got the column actually defined in our table because we've got a migration. So when we deploy this to production, we've got the column in the database. We can store data in there. We can start writing queries against it. But now we go back and look at our ticket. Remember the ticket said, oh, we need to be able to search for users with a given amount of courage. Maybe we want to search for users with 0 courage to find the lion. So we better add an index. We go back to our model, index equals true. We've asked for an index on this column. Great. But then the tornado alarm goes off, our house flies away, we get into a bit of a fluster, and we forget to create the migration. So now we've got a model that says we want an index, but we don't have a migration that creates the index. And if there's no migration, it's not in our production database. So we've got that mismatch. But we didn't realize, and in code review, we got distracted, no one noticed. We deployed it to production. Things are sort of working, but like the database server is chugging. There's performance incidents. People are running around with their hair on fire. Lots of screaming. Dorothy comes up to us and tells us we should be ashamed of ourselves. And we say, no, let's learn from this experience. What can we do better? Well, we could have the computer tell us about this mistake. And that's what we do. So we have just a normal automated PyTest test migrations match model. And that test will manage 2 databases internally. So this won't do any of the transactional magic we talked about before. This is a special test. So it's created 2 databases within our Postgres server. One of them, it initializes from models. So it takes our models and just splats them in there. The other one, it initializes from migrations. So it starts at the first migration, runs all the way through to the final migration. We've now got 2 Postgres databases that have the schema that we think we should have from 2 different sources. If Postgres thinks the schema is something, that's kind of the source of truth. Like that's how the data is actually managed. So thinking about the Postgres schema is useful. We can get Postgres to print that out, pgdump schema only. That's a utility that comes installed with Postgres. That gives us a big string that's a whole bunch of like create table, create index statements. With that string, we can just compare the strings. Check that the two different ways of getting the schema matches. We've now done this, and when we run the test, normal PyTest, test migrations match model, there's an assertion that fails. And the assertion, like the error message, tells us, oh, there's a missing create index statement. This is a contrived example. With a more complicated example where you're having to handwrite a migration, it's particularly helpful. But just to be aware, this only helps with schema migrations, not data migrations. Thank you for listening. We can now all fly back off to Omaha, or maybe just to lunch. Hopefully you learned something. I don't think we have time for questions, but find me if you do.
We do not. It is almost lunchtime. Please, everyone, join me in thanking our speaker. And here is your lovely mug.
Thank you.